Hello there, young students of AP Chemistry. This is a short recording about something called the common ion effect. So what we're doing is we are considering what will happen to a weak acid or a weak base if we add a common ion to this. Now you already know a little bit about what's going to happen because you have studied Le Chatelier's principle in our first unit of equilibrium. So let's just talk for a minute about this 0.1 molar acetic acid that's been provided here for you. If you have 0.1 molar acetic acid and you go ahead and write the equation and then ice and solve for X to get the hydronium concentration, you will calculate a pH, of 2.87. Now what if we take this weak acid and we add this salt, sodium acetate? We know that there's two ions that we're adding to the solution. If that salt dissolves, which it will, we're adding sodium ion and we're adding the acetate ion. So if we look at our equation for our weak acid, we can see that sodium is not a common ion. There is no sodium in any of these compounds. So we can ignore the sodium ion. However, acetate is present in the equation, and that is our common ion. Now let's consider what's going to happen if we add sodium acetate to a solution of acetic acid. We have added the acetate ion, which is a product species. According to Le Chatelier's principle, if we add products to a system that is already at equilibrium, it's going to use those products that we give it, which means the reaction, instead of running, it's at equilibrium, is going to run in the reverse direction. By running in the reverse direction, it's using acetate and making acetic acid. So let's consider what's going to happen. If we know that it's going to shift or run in the reverse direction, shift to the left, what's going to happen to the concentration of a hydronium ion? Here, if you think about that for a minute, and then think about what's going to happen to the pH. Hopefully you thought about it, and you would recognize that the concentration of hydronium ion will decrease as the reaction uses products and makes more reactants. And if it's going to decrease, the pH therefore is going to increase. So once we add sodium acetate to our 0.1 molar acetic acid, the pH will no longer be 2.87, but something higher than that. So let's go ahead and calculate. What we have here is our 0.1 molar acetic acid, and we're adding to that 0.05 molar sodium acetate. You could also do this with a solid and figure out the concentration once that solid dissolves, but I've been kind and given that to you already. So I'm just going to rewrite the equation here for our equilibrium scenario. Now we know that the Ka for acetic acid is 1.8 times 10 to the negative 5, and that will determine I better write that up here. That will determine the extent to which the forward reaction goes. So let's consider our ice chart. We know that initially we have 0.10000 molar acetic acid. And we know that initially we also have 0.0500 molar of sodium acetate, of which there's a common ion, acetate. So 0.0500 molar here. And we have no hydronium. So what's going to happen here is that we know this reaction is going to run this is going to go down by an amount X. I don't want to talk about going in the reverse direction here, but we know that the pH will go down because there will be less hydronium than without the sodium acetate. This will go up by an amount X, and of course up by X. So if we write our equilibrium constant expression, Ka equals the concentration of hydronium times the concentration of acetate ion over the concentration of the acetic acid. So we know that 1.8 times 10 to the negative 5 is equal to X times 0.0500 plus X. I forgot to do the E part of the ice chart. Over 0.100 minus X. Now, we should always start by neglecting the change in X. So this X approaches 0. We'll ignore that. And then go ahead and solve for X. So take a minute to do that. I'm getting the value for X, which remember is equal to the concentration of hydronium ion, which is what we're interested in here, is equal to 3.6 times 10 to the negative 5 molar. And from that, we can calculate the pH. Remember that we'll keep the same number of decimal places as we have significant digits. We have, actually I made that 2 significant digits because of the value of Ka that I was using. So 2 significant digits means we'll keep 2 decimal places in the pH, 4.44. Now, according to Le Chatelier's principle, we had predicted that the pH will increase from the 2.87 that we originally have with the acid alone, and that is the case. When we have the acid mixed with the salt, sodium acetate, the common ion causes a shift in the equilibrium, and the pH will increase because the concentration of hydronium ion has decreased. Now let's consider the equilibrium with the sodium acetate. We know that sodium acetate is a basic salt because sodium hydroxide would be the parent base, and which is strong, and acetic acid is the parent acid, which is weak. So we have our equation for a Kb, right? We know that we can get Kb for acetate by dividing Kw by Ka for the acetic acid. So if we add acetic acid to it, what we've really added here is not a common ion, but a common species, because acetic acid doesn't ionize completely. We're not adding hydronium. What we're adding is the weak acid, acetic acid. So what we've done is we've, again, added a product. This is going to cause the equilibrium to shift to the left. Remember that according to Le Chatelier's principle, if we give a system at equilibrium some more products, it's going to run in the reverse direction to use that product and thus make more reactants. We know that the hydroxide then concentration is going to decrease. And if the hydroxide ion concentration is decreasing, that means that the hydronium ion concentration is increasing. With more hydronium, the pH will also increase. Now, I did not calculate the pH of the 0.05 molar, of the 0.1 molar acetic acid before I started that. Oh, you know what? I did. This pH is 8.87. So without anything added to the sodium acetate, 0.1 molar sodium acetate has a pH of 8.87, and we would expect that pH to go down. So let's do the calculation. We have acetate interacting with water to make hydroxide. The Kb, once you calculate it, is 5.6 times 10 to the negative 10. We know that our ice chart, we're starting with 0.1 molar sodium acetate. Sodium is spectator, so we ignore it. And we're starting with 0.05 molar acetic acid and no hydroxide. We know that this concentration of acetate ion will go down, and these concentrations will go up by the value x, which means at equilibrium, 0.1 molar minus x. I know this is old hat here. 0.050 molar plus x and x. And then we will solve our equilibrium constant expression. Good idea to write that out if you are being judged on your work, and you are always being judged on your work, even if it's from afar. And now we can plug and chug. We'll substitute our values into our algebraic expression. So 5.6 times 10 to the negative 10. Kb equals x times 0.050 plus x divided by 0.10 minus x. And of course, we are going to neglect the change in x and say that that approaches 0, and it's so small, it's not going to change those numbers. And in doing so, we can solve for our concentration x, which we know is our hydroxide ion concentration. So take a minute to do that. I'm getting a concentration of hydroxide to 2 significant digits, 1.1 times 10 to the negative 9 molar, and therefore the pH is equal to 14 minus the opposite of the logarithm of 1.1 times 10 to the negative 9 molar. So pH is equal to, oh dear, I think I just solved for the pOH. pH is equal to 5.04. And we predicted that the pH of our salt, sodium acetate, which was 8.87, would, we predicted increase. Oh, no, we didn't. I was wrong. I'm sure you caught that. So when the hydronium ion concentration increases, you guys know, the pH decreases. So now we have predicted properly that the pH of the salt by itself, 8.87, is going to decrease with the addition of the acetic acid, and it does to a pH of 5.04. So that, my friends, is the common ion effect. You should have a problem set for your common ion effect that you should take some time to work on now. It just says on it the common ion effect. It does not say problem set. And you will be quizzed on that tomorrow.